Hello everybody, my name is Dmitry Podoskuyev. I'm a production engineer at Facebook, and today we are going to talk about protecting system integrity using trusted platform model. In order to make the talk more practical, I'd like to build it around demonstration. I'll be using a simple setup which consists of Linux container and QEMU virtual machine with Linux. I'll try to give some background information about trusted platform model and measured boot, but it's really a bare minimum. I'll give some pointers so that you can get started and learn more if you are interested. So the talk is meant to be a starting point for experiment in this area. Most all the things are easily reproducible on your laptops or servers, so if you want you could try it yourself and ensure it works. All the code is pretty simple and easy reproducible. Okay, let's move further. So the plan is simple. Describe our experimental environment, show how malicious firmware can compromise your secrets, try to figure out how measured boot and trusted platform model could help us to deal with it, and of course answer your questions. Let's get started. Our setup consists of a container and QEMU Linux VM, which communicates with the container through Linux top network device. In the container we have the DHCP server running, which provides a virtual machine with IPv4 address, and software TPM simulator, which VM is using instead of hardware one. To save time, I'll skip some long processes like virtual machine reboot and firmware build, but I think they are not so interesting anyway. Okay, our VM is booted using non-compromised firmware. Let's create a super secret text file on the root ext4 partition. Here is our file. Moving to the root. Checking. Okay, looks good. Seems to be fine. Okay, so we have our secret file on the root partition now. Let's add a tiny DXC driver to our firmware image. Objective of the malicious DXC driver is to get the secret and send it over the network. First of all, it scans all partitions and tries to find the flag.txt file which we just created. Then it queries the DHCP server for IPv4 address and uses the network configuration to send the secret to some kind of external server. Now let's boot our virtual machine using the compromised firmware image. Okay, starting our software TPM, starting the machine itself. And here we can see the malicious DXC driver at work. It kindly reports everything it does, but a real malicious DXC driver will be less kind, of course. So first of all, it starts to scan available partitions at the first line. At line 2, it skips the first partition because it's a UEFI FAT partition. On the second partition, which is ext4 root, partition, it finds the flag.txt file, it's line 3, and since the file is found, it continues with the RCP v4 query. These are lines 4, 5, and 6. The DHCP query was successful, and the DXC driver sends content of the secret file to a simple Python HTTP server running in the container. These are lines 7, 8, and 9. Of course, the sequence could be different. For example, the driver could fetch some file from the network first and put it somewhere, for example, in etc directory. Okay, key facts about our malicious DXC driver. It's created using EDK2, an open source firmware development framework. I'll say a few words about it in the next slide. It's about 700 lines of C code, and it supports DHCP versions 4 and 6. It's around 16 kilobytes in the compiled form and requires around 200 kilobytes of support drivers, kind of libraries. It's tested on real hardware and works just fine. A few words about EDK2. It's probably the most popular open source framework for UEFI development. Among other things, it contains everything one needs to write a DXC driver. It worked fine for us in this experiment. This is open source UEFI. There is an open source UEFI implementation named Tian Core, which is based on EDK2 framework. Tian Core documentation contains a great UEFI driver writer's guide with lots of examples. It's available at GitHub. Could be a great starting point for UEFI driver experiments. Someone could say that there is a secure boot technology which would prevent the malicious firmware from being executed at all. So we probably shouldn't care. It definitely works good with something like a personal laptop, but there are some considerations which should be taken into account when we work at scale. First of all, failed firmware signature check usually means that the server cannot boot at all. And the reason of the failure is not necessarily security related. It could be a human error or even just a flash memory bit flip. Of course, flashing from BMC could be used in order to recover firmware, but usually it's not something that we use on daily basis. How much time would it take to reflash a significant amount of machines? Or how have we tried it ever? These are the questions which could be raised in this regard. The second point is that secure boot by itself doesn't provide a way to make sure it's enabled and works properly. Someone with privileged access could disable it on a few servers with compromised firmware and leave the company. How often do we check that secure boot is actually enabled on each host across the fleet? And even if we do it often, how could we be sure that compromised host didn't fake the results? Fortunately, there are other ways to ensure system integrity and prevent malicious firmware from accessing our secrets. And today we are talking about measured boot. The idea behind measured boot is very simple. Just calculate a hash, in other words, measure, of all critical code and configuration used during the boot process. But there are a few questions to consider. Boot process is complex and not all the parts are available at the same time. To address the issue, we can make each part of the boot chain to measure the next one before transferring execution to it and extend the existing hash with the one just calculated. This way we can build a hash which depends on all components of the boot chain. The second question is, how can we trust the first element of the measurement chain, also known as the root of trust? The good news is that it can be very small, thus has very little attack surface. In some devices it's implemented as the code in read-only memory, but often it's a small piece of code signed by hardware vendor and checked by hardware with the burned sign-in key. For Intel-based systems, it's often Trusted Execution Technology or CBNT for newer generations, but of course it could be a dedicated chip or other solution. In our setup, firmware itself is root of trust. It's absolutely insecure, but it's probably enough for the demonstration. Another ingredient of the measured boot process is the storage of measurements. It has to protect them along the boot process and prove their integrity. Trusted platform model is one of the most popular choices for this role. Trusted platform model is a hardware model which implements corresponding specification of trusted computer group. It's a pretty complex device, but in context of measured boot, we are interested only in a few of its features. The first one is the platform configuration registers. They are just memory areas which cannot be written directly, but only extended, as described in the previous slide. PCRs is the storage which boot chain components use to store measurements they've made. Since each new PCR value depends on the previous one, and the registers cannot be written directly, the final value reflects the state of the whole boot chain and cannot be tampered. The second feature is TPM's ability to export PCR values signed by a key which can be verified using the certificate chain up to a vendor's certificate of authority. In other words, we can prove that these particular PCR values are calculated by a certain TPM, and the vendor guarantees its cryptographical properties. These TPM features in combination with measured boot gives us a way to get cryptographically proven data about booted system state. This data could be checked remotely, which is also known as remote attestation, and locally by TPM for system state dependent encryption, also known as sealing. So in the ideal scenario, we could do the following to protect our secret file. First of all, do remote attestation. In other words, ensure that the system is booted to a known good state. Then deliver the secret to the system using encryption key, which is guaranteed to be available only to the system in the known good state. Then encrypt the secret locally in a way it could be decrypted only when specific policy is satisfied, also known as sealing. We will use TPM signed policy for these purposes. It allows us to unseal the secret not only in certain system state but in any system state signed by a certain authority. It's pretty important because of potential huge number of good system states. Since sealing process produces a signed PCR value set, also known as quad, we also can make sure that the system was in the certain state during this process, and the state matches 1 during attestation. Deliver a signed policy which allows the secret to be unsealed in desired system state. It can be bound to a particular system or be valid on any system in certain state. And finally, we can use the signed policy to unseal the secret after system reboots. Unfortunately, it would take a lot of time to demonstrate the full flow, so we'll focus on key points, which are basically sealing and unsealing. Okay, let's start our data sealing adventure. It's possible to seal the secret to certain set of PCR values, but it would force us to reseal the secret to every new good system state. To overcome this, we will use the policy authorize, which can be satisfied by any policy which is signed by a certain key. Here we'll generate a key which will be used for policy signing. The key's name is the hash of public part and can be calculated without TPM. So let's do it. We'll hold our policy signing key in the separate directory. Let's generate an RSA key. Here it is. And load it to the TPM. We don't need a context at the moment. Okay, now we should generate an authorized policy. Policies are hashes of special policy state, but they are not bound to a certain TPM, so can be created without it. Basically, both steps can be done once for all hosts we have. Okay, let's create authorize policy. Starting our session, the trial session. And removing out of context, we don't need it anymore. Okay, the next step is sealing itself. Sealing is wrapping a secret with a TPM storage key, which belongs to one of TPM's hierarchies. So the first thing to do is to create a storage key. In this demo, we will use endorsement key. Endorsement key is a special storage key which is usually certified by manufacturer. The key is derived from endorsement hierarchy primary seed in a deterministic way, so it can be regenerated as needed. But hardware TPMs are pretty slow devices, and key derivation often requires a few seconds, so it makes sense to preserve the key in TPM's non-volatile memory in some cases. Okay, let's create a key. key is generated. The default policy of the endorsement key is to use auth value of endorsement hierarchy. In our example, the auth value is empty, so we don't need to provide it at the moment. So as you can see, I haven't provided the name, and here we actually sealed the secret. As you can see that our secret has two parts, private and public, as all TPM internal objects do. As an additional artifact of sealing, we could get a quote, a signed set of PCR values and some other values like boot counter. So let's make sure that it's actually encrypted. Oh, and it is fine. Now we have to create a PCR policy which matches our known good system state. First of all, we should find PCR values which match desired system state. Ideally, they should be calculated from known good system artifacts using algorithms they use to make measurements. Next, we have to generate the policy itself and then sign it with our policy signing key. Let's do it. Reading current PCR value. Starting our session. It's trial session again, and we created a PCR policy, signing the policy with our signing key. And we can remove context. And finally unsealing the secret. It's a little bit longer than we could expect. First of all, we should check that our PCR policy is signed with the right key, then satisfy both policies, load the secret to TPM, and finally unseal it. Let's do it. Load in our policy signing key, verifying signature. We got a verification ticket, and we don't need this context anymore. Starting policy session. Both policies are satisfied. We should recreate our endorsement key in order to load our sealed secret. We don't need these contexts, and boom, it works. We unsealed the secret. And now let's boot the machine using compromised firmware and check that we cannot satisfy the PCR policy anymore. Let's print the last PCR, old PCR0 value, and the current one, and they don't match. Trying to satisfy the policy, it cannot be satisfied. Cleaning up a bit, and that's it. It's question time. Thank you very much for your attention. I have to admit that measured boot and TPM applications are very broad topics, and it's very hard to describe even a tiny bit of them in 30 minutes. But I hope that the talk will raise some interesting questions. If some of them are ready to be asked now, I could try to answer them. If not, there is my mail. Feel free to contact me in this regard. Thank you.